Alright, so one of the last things that we covered last class period, we were going over inverses. I told you that the natural log of e to the x was equal to x, and e to the natural log of x is equal to x. So that means that e to the x and natural log of x are inverse functions. Okay, so what does that mean? That just means that the domain of one is equal to the range of the other, and the range of one is equal to the domain of the other. So we can solve exponential equations, like say this here. So I had 10 equals e to the 2x plus 1 power, and I wanted to solve for x. Then I can solve this just using algebra. I'm actually just going to use the inverse function. If I take the natural log of both sides, so I'd have the natural log of 10 equals the natural log of e to the 2x plus 1. Then what that does is that allows me to move this power here in front of the natural log. So I have the natural log of 10 equals 2x plus 1 all raised to, times the natural log of e. Okay, so if I want to solve for x, there's a couple of ways that I can do that from here. Just solve the equation by whichever way you feel the most comfortable in doing. But the natural log of e, remember, is just going to be equal to 1. So I really just have natural log of 10 equals 2x plus 1. So subtract 1 from both sides. That's not going to give me the natural log of 9. Don't even try that. It's natural log of 10 minus 1. Okay, equals 2x. So x equals natural log of 10 minus 1 all divided by 2. And you could get a decimal for that. I'm not sure exactly what it would be, but you can get a decimal by just working out the numerator and then dividing by 2. So that is an exponential equation that we used its inverse natural log to help us solve. You could also have a natural logarithm problem, like say the natural log of 2x minus 3 equals 5. And you can use the reciprocal of natural log to help me solve this. The way you do that is you say e to this power on the left side and e to this power on the right side. Once you have the same base on each side, then what is that going to do here? If you have e to the natural log, the answer is just all this right here. So the left side becomes 2x minus 3. The right side is just e to the 5th. So remember, e is a transcendental number like pi. And if your calculator has an e to the x button, that is that exponential function, e to the x. That's how you evaluate it. Alright, but say plus 3, so 2x equals e to the 5th plus 3, divided by 2, divided by 2. So there's my answer. You can find a decimal for it in your calculator, put 5 e to the x, or e to the x, then 5 in there, plus 3, whatever that gives you, divide it all by 2, you got your answer. 75.70. Okay. 75.70. Sounds good. All right. Remember how e to the x has to work, because e to the x, or e to some power, let's say I had e to the second power times e to the third power. So remember, that's the same base, so if you ever run into something like this, then you just do what? Add the powers. So it's going to be equal to e to the fifth power. Same base, add the powers if you're multiplying. Alright, if for some reason or another you ever have, say, e to the 5x over e to the 2x, treat it just like you would if this was x to the fifth over x to the second. Subtract the powers. So that's equal to e to the 3x. So as long as the base is the same, if you have a quotient like that, top power minus bottom power. Now, it is acceptable also to leave a final answer like e to the negative 2x. That's okay. But if you have e to the negative 2 with no variable, then you want to write that as 1 over e squared. So that does matter. Where if it's with a variable, it's just so common that we could just leave that as e to the negative 2x. It's kind of strange, but that's just the way we do it. Alright, the graph of e to the x, just real quick, I can pull that up. And let's see what's happening. Now remember, e, we said it's a number. So like, I believe it's 2.71828 something, 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 something. It keeps going on and on. So I guess it's a little different from pi in that aspect that we have e to the x. We don't have pi to the x, right? We don't use that function. It probably could be used somewhere. But the transcendental number e usually is used with a power of x, or some power times x, or some number times x, I'm sorry, as the power. So let me just throw this in here real quick. So I want to graph e to the x. Alright, it's real hard to tell what's going on here, but you do see this line here, it's going down, 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 and it never crosses this axis. It just gets closer and closer to this x-axis. It never touches it, it never crosses it. This right here, as your x's get larger, it goes up, up, up really fast. So it looks like as x goes to positive infinity, meaning as x gets really, really big, the y's are also going to get really, really big. So as x goes to positive infinity, e to the x also goes to positive infinity. As x goes to negative infinity, meaning your x's get smaller and smaller and smaller, what will your y's approach? 0, right? It never crosses this line. It just gets closer and closer to it. So like, you won't get any negative numbers out when you plug in, even if you plug in x equals negative 100. So like, say I wanted to calculate that. Say e to the I'll try. My mouse is double clicking. Well, believe me when I tell you e to the negative 100 is really, really, really small and close to 0. But e to the 100 would be really, really, really large. Okay?
E to the negative 100 is 3.72 times 10 to the negative 44.
So it's really, 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 really small. E to the negative 100?
Is 3.72 times 10 to the negative 44.
3.72 times 10 to the negative 44. That's a pretty small number. You say 72? That means that I would need to move this decimal place over 44 places to the left and start putting zeros. So you see it gets really close to 0. And then e to the 100th is what?
E to the 100?
Yeah, try that one. That's
2.68 times 10 to the 43rd.
alright, so yeah, I'd have to go 43 places to the right. So that's pretty crazy. Alright, I guess the most interesting and probably the most useful thing about the exponential function is that the derivative of the exponential function e to the x is itself e to the x. Of course, that will change just a little if your power changes. Like say I had the derivative of e to the u. So it's something other than just x. Then that's going to be equal to e to the u times the derivative of that u. So for example, let's say I have y equals e to the 3x. What is my u equal to? 3x. So my du then would be equal to 3. So if I want to take the derivative, that's going to be e to the u du, or e to the 3x times 3, because the du is 3. So that is 3 e to the 3x. This is probably the easiest derivative of any function that we take. Take the derivative of the power and multiply that times the original. Now most of the time when you multiply it, just put it in front. Like, you know, I wrote it behind here. That just doesn't look right. And just put it in front. So let's say that I had e to the x squared minus x power. Let me make that y equals. My u equals x squared minus x. So my du equals 2x minus 1. So that's what I multiply times my original. So put that in parentheses though. Alright. So the u is the power, or the exponential part. The du is the derivative of that. You say that times the original. When you go from here to here, you cannot change the power. Just like with trig functions, when you take derivatives and integrals of trig functions, you can't change what you're evaluating. That doesn't change. What changes is, you know, depending on the du. let me do one more of those. Say that I had f of x equals x e to the negative 1 over x power. And I wanted to find the first derivative. When you have two terms like this side by side, what do you have to use? The product rule for derivatives. So that is the first term, so x times the derivative of the second term. I'm just going to write down derivative of the second term. And I'll come back and do that. Plus the second term times the derivative of the first term. That's the product rule for derivatives. I think that's covered maybe in about section, I don't know, 1.5 or around there, somewhere in chapter 1, or maybe the beginning of chapter 2. That sounds better. Alright, but we have to be careful when we take this derivative here, because the power there is negative 1 over x. Alright, so that means when I take this derivative for this part, I have to let u equal negative 1 over x. So what's the derivative of that? Well, you want to think about that like it's negative x to the negative 1. Right? Because if you bring that x up, it becomes a negative 1 power. So now take the derivative. Don't add. You have to say, well, you say the power times what's in front, and then subtract 1 from the power. So that's going to be 1, and then x to the negative 2, which is 1 over x squared. Alright, so now we can finish this derivative because the other derivative we take is pretty easy. So this first term here is going to be x, and then what's the derivative of this thing? It's going to be 1 over x squared times e to the negative 1 over x. Right? It's the derivative of the power times the original. Plus e to the negative 1 over x times the derivative of x. What is that? 1. Now I have x times 1 over x squared times e to the negative 1 over x. So what cancels out? This x is going to cancel one of those x's out, right? So I have e to the negative 1 over x plus e to the negative 1 over x. It is totally acceptable to leave those e's as negative powers. That will be okay. However, when you have that in two terms, the best way to write is to factor that term out. So that would be 1 over x plus 1 in parentheses. That's the most correct answer. That's the best way to write that answer. So that's the derivative of e to the x. What about the integral of e to the x? Well, since the derivative of e to the x is e to the x, the integral of e to the x is also e to the x, plus c, of course. So the integral of e to the u, as long as you have the du, or you've adjusted for it, is equal to e to the u plus c. Alright, so for example, let's say that I wanted to integrate e to the 3x dx. And the first thing I do is I write my u down. U is equal to 3x. So what is du equal to? 3. The derivative of 3x is 3. So there cannot be an x in front of the term or below the term. To adjust for the 3, we bring out a 1/3. So we have 1/3 times the integral of e to the u du. Or 1/3 times e to the u plus c. And what was u? 3x. So that's 1/3 e to the 3x plus c. Alright. Let's look at another. Let's say I had x e to the x squared dx. Now, never try to simply integrate each term in a row. You can't do that. You have to look for a u and a du or a way to manipulate and do algebra. So for this one, if I let u equal x squared, then that makes du, the derivative of u, equal to what? 2x. Notice that there is an x to the first here, and there is an x to the first in front of it. That's good. That's what you want. That's what you have to have in order to integrate this. If this x was not in front of it, if it was just the integral of e to the x squared, I have no idea how to do that integral. E to the x squared, not a clue. So make sure that you do have the du. Now there's a 2 right here. I saw some people like to take this 2 and multiply it times 2. That's what we do with derivatives, not with integrals. We need to bring out a what? 1/2. So this is 1/2 times the integral of e to the u du. Okay, so that's 1/2 times e to the u plus c, or 1/2 times e to the x squared plus c. Okay. All right, I want you to try a couple of these derivatives and integrals. Let's find the derivative on a couple. Let's say I had y equals 5e to the x squared plus 5 power. Try that one. Let's try y equals x squared e to the negative x power. And then, since some of you are really wanting to do some quotient rule as well, which I don't blame you, I like doing quotient rule. It's e to the 2x over e to the 2x plus 1. Alright, so let's try to find those 3 derivatives. After we get through those, we'll practice with some more integrals. Alright, so if I want to find the first derivative, this first one here, I have a constant in front. Remember, you just bring constants down with the first derivative. and then the derivative of this term, my u equals x squared plus 5, so my du is going to be equal to 2x. Alright, so the derivative of e to the u is e to the u du. So I'm going to have to say it times the du. I'm going to write that first, and then I'm going to write the e to the u second. Alright, so that's 10x e to the x squared plus 5. Alright, for this second problem here, since I have a product of these two variable functions, I'm going to say, you have to say the first times the derivative of the second plus the second times the derivative of the first. So the first is x squared. The derivative of e to the negative x, your u is negative x, so your du is negative 1. So you're going to have to say this, e to the u, times negative 1. So it's just going to make it a negative e to the negative x. Okay, so this is first times the derivative of the second plus the second times the derivative of the first. The derivative of the first is 2x. Alright, so this is going to be negative x squared e to the negative x plus 2x e to the negative x. This answer is okay, but I can write it in factored form. So I can factor, I'm going to factor out a negative, since my first term is negative. I'm going to factor out an x to the first, since I have an x to the first and an x to the second. And I'm going to factor out an e to the negative x. Let's see what that leaves me with. I should have something real pretty here in these parentheses. So that's going to leave me with a positive x to the first, then minus just 2. So I say something really pretty. It was just kind of simple, like a real simple binomial there. It would not have been wrong to leave it this way. Alright, so now let's find the derivative of this quotient. So the quotient rule is the bottom, or the denominator, times the derivative of the numerator, and the derivative of the numerator, if your u equals 2x, your du equals 2, and so you just say du times e to the u, so that's going to be 2e to the 2x, right? So that's the bottom times the derivative of the top minus the top times the derivative of the bottom, and the derivative of the bottom here, you just have to take the derivative of the first term because the second term is 0, so that's going to be the same, 2e to the 2x. Same thing we got when we took the derivative here. You get the same thing there. Over the denominator squared. Alright, so I need to multiply out my numerator so I can simplify. Multiply out things like I should. Now when you multiply 2e to the 2x times e to the 2x, you have to add those powers. So it's going to be 2e to the 4x, then plus 2e to the 2x. Now multiply those two together, so it's going to be minus 2e to the 4x. Again, you have to add those powers, over e to the 2x plus 1 squared. You see these two terms cancel out. I'm just left with 2e to the 2x over e to the 2x plus 1 squared. So I want you to try these three integrals. Let's try the integral of e to the 1 over x squared all over x cubed dx. The integral of e to the 4x over 1 plus e to the 4x dx. I really like that problem. And how about this one? The integral of e to the 2x plus 2 e to the x plus 3 all over e to the x dx. So work on those three problems really quick. So in this first one here, let's let u equal 1 over x squared. So then that's the same as x to the negative 2. So your du would be negative 2x to the negative 3, or negative 2 over x cubed. You see this x cubed is right here. It's in the denominator just like it is in the du. That actually has to be there for me to be able to integrate this. So the only thing I have to do is adjust to this negative 2. So I need to bring out a negative 1/2. So this is negative 1/2 times the integral of e to the u du. So where is the x to the 3 in the denominator? It's in the du. Alright. So that's equal to negative 1/2 e to the u plus c, or negative 1/2 e to the 1 over x squared plus c. Alright, this next one here, anytime you see a fraction and the denominator and numerator are kind of similar, maybe off by 1 power. In this case, since they're exponentials, I see the same term here and here. Then if I let my u equal 1 plus e to the 4x, my du would be equal to, the derivative of 1 is 0. The derivative of e to the 4x is 4e to the 4x. Because if I let this be my u, my du is 4. Alright, so the derivative of e to the 4x is 4e to the 4x. Okay? So that is letting the entire denominator be my u. I have this du. If you look, this part here is already present. It's there in the numerator. The only thing I have to do is adjust for that 4. So bring out a 1/4, and now this is in the form 1 over u du, because I let the entire denominator be my u. And that's a natural log integral. So that's equal to 1/4 natural log absolute value of u plus c. So that's 1/4 natural log absolute value of 1 plus e to the 4x plus c. Okay.
We're answering questions for you, please.
Alright, on the third one, letting the bottom be my u and finding the du does nothing, because I have more than just e to the x up top. So there is no u up here that I could take to have the du in the bottom. So what I would need to do is do some algebra first. So I would do term-wise division first. So say this over this, plus this over this, plus this over this. Rewrite that integral. So it'll be the integral of e to the 2x over e to the x, plus 2e to the x over e to the x, plus 3 over e to the x dx. And now simplify. You can subtract the powers here, so that's going to be just e to the x. These actually cancel out, so it's going to be plus 2. This one here, plus 3, I would bring that to the top. But remember, when you bring it to the top, you have to change the power to negative x. If that's a positive 1x in the bottom, it'll be a negative 1x in the top. Now we can integrate each term separately. The integral of e to the x is e to the x. The integral of 2, make sure you don't just write 2. It's 2x, right? Because the derivative of 2x is 2. And now on this last one here, your u is negative x. So your du is what? Negative 1. So I just need to bring out the reciprocal of negative 1, which is negative 1. So it's going to be minus 3e to the negative x. This 3 just comes down. The minus is from the du. Then plus c. Okay? So, all right, let me work. Of course, there has to be some kind of trig somewhere, and you almost have to just muscle trig into one of these integrals. Here's one. E to the 2x times the cosecant of e to the 2x dx. So it's not very, I guess, very intuitive how to do that integral if you let trig just scare you to death, because, well, where did that trig come from? Well, that's a crazy looking function. I really don't know what that would model, but maybe it would model something. The key is pick the u so that you have the du. And so if I let what I'm evaluating cosecant at, if I let that be my u, then my du is equal to 2e to the 2x. And so I have e to the 2x in front, which I would have to integrate this. So you bring out a 1/2, so it's 1/2 times the integral of cosecant of u du. So that changes the problem totally into something that that I've seen before a few class meetings ago, I'm sure, maybe 1 or 2. The integral of cosecant of u. The integral of cosecant of u is negative natural log cosecant u plus cotangent u plus c. It's 1/2. It's negative natural log cosecant u. What was my u again? E to the 2x plus cotangent u, which is e to the 2x plus c. Okay, so definitely not a very, I guess aesthetically not very beautiful, but if you like trig, you're wondering where it went, I found one for you. Alright, now so all of these derivatives and integrals that we've done with natural log and with e to the x, the base of the natural log is base e, the base of e to the x is base e. Well, what if we have a different base? What if we have log base 2? Or what if we have log base 10? We do have a formula, or we have formulas for the derivative of bases other than e. Now, these are not used all the time, not in calculus. So, you know, I would definitely write these down. If you would have come to me this morning and you would have asked me the formulas, there's a 50-50 chance I would have even known them, because I never write them down that much, or I don't use them that much. Even application problems, I just don't. They're not found in the things that I've done. Now, does that mean they can't be applied? No, I'm sure there's a billion ways to apply these. But if we have bases other than e, so I'm going to say derivatives of bases other than e. If I have the derivative of some number, some positive real number a to the x power. So that could be 5 to the x, 10 to the x, 0.2 to the x. As long as it's not 1, because we don't like 1 to the x, it's, you know, because that's going to be 1. But any positive real number, then the derivative of that to the x power is equal to the natural log of a times a to the x power. So if y equals 2 to the x, the derivative of that would be the natural log of 2 times 2 to the x. Not a very complicated derivative. Now if it's a to the u, so let's say I had the derivative of a to the u, so that's something other than x, right? I bet you could figure this one out if you thought about it for a second. Natural log of a times a to the u times, what do you think? Du. You got to take the derivative of that u. That's basically the same as e to the x, except you got to put that natural log of a in front. Okay, so let me throw out, or let me throw in an example. Let's say that it was y equals 2 to the 5x power, so something other than just x. And I want to find the first derivative. So my u is 5x, which makes my du equal to 5. Alright, I'm not doing an integral, I'm doing a derivative. So the first derivative would be natural log of 2 times 2 to the 5x times 5, which I would not leave this 5 behind the exponential function. I would write this as 5 times the natural log of 2 times 2 to the 5x. Alright, so that's how you take the derivative of something other than e to the x power, or some power, some variable power. Now, if we want to take the derivative of log base a of x, that's equal to 1 over natural log of a, excuse me, natural log of a times x. that x is in the denominator. So 1 over natural log of a times x. And then, of course, anything we can do for x, we can do for u, not y-o-u. What can I do for you other than annoy you with calculus? Alright, so if I want to take the derivative of log base a of u, and let's see if we can figure this out. If it's just like the one above it, except we have a u. 1 over natural log of a times u, and then what do you think you're going to have to say this whole thing times? Du. So depending on what your u is, let's put your du right there. Okay. So how about I do one of these? Let's say I have y equals log base 10 of cosine x. Alright, so the derivative of this is going to be equal to 1 over the natural log of what? 10 times, what's my u in this? My u is cosine x. So I didn't write that down, but you could see that. And what's the du? Negative sine x. So this is negative sine x over natural log of 10 times cosine x. Or, what's sine over cosine? So that's going to be negative tangent of x over natural log of 10. Since I'm multiplying, I can just say sine over cosine is equal to tangent. Alright. So that's derivatives of bases other than e. Then of course where there's any derivative there's always an integral. But just make sure you know, if you have a u, you have your du type stuff. There is a formula if you want to write this one down. The integral of a to the x dx is equal to 1 over natural log of a times a to the x plus c. So if I wanted to integrate 5 to the x, that's going to be equal to 1 over natural log of 5 times what? 5 to the x plus c. How is that different than the derivative? Let's see. When we took the derivative of 2 to the x, we got natural log of 2 times 2 to the x. The integral, you get 1 over natural log of 5, so that's like that reciprocal times 5 to the x plus c. As long as you follow these formulas, you should be good with these derivatives and integrals. They're kind of similar to the e to the x derivatives and integrals. just a little different. One place that you can get e to the first power is by looking at the limit. If you remember limits, the limit as x approaches infinity of 1 plus 1 over x all raised to the x power, believe it or not, is equal to e to the first power. Kind of strange that it is. I could show you why, but it's probably just a little bit further than our scope of things in here. But it's definitely neat that that is true. You can even relate this over to compound interest. The formula for compound interest is similar to that, and an actual compound interest can be found. Do you remember, can't remember all the different formulas, but if you have, what is this? This would be like, you could say your balance in the bank is equal to principal times 1 plus rate divided by the number of compoundings per year raised to the number of compoundings per year times time, number of years. This would give you like how much would be in your bank. And so it does make a little bit of difference, like if your money's compounded twice a year, 12 times a year, 4 times a year, 3 times a year. If you hear that, you know, it's compounded quarterly, compounded biannually, you know, or maybe it's compounded continuously. The way that you compound continuously is P times E to the RT power. So there is a little bit of difference in those two different compound interest formulas. If you compound continuously or monthly, your book gives an example of that just so you can kind of see the difference. I'm not going to test you on this. It's just kind of neat to see that you can look right here. If you make a deposit of $2,500 into an account that pays an interest rate of 5%, an annual interest rate of 5%, find the balance in the account at the end of 5 years when the interest is compounded quarterly, monthly, or continuously. And so if you put in how much, you know, how much money you put in, the principal and the rates and the time and everything, and you compound quarterly, then you have $3,205.09 compounded monthly, $3,208.40, or compounded continuously, $3,210.06. So there is a little bit of difference in how your money's compounded, how much money you would have. So it's kind of neat.